Assalamualaikum and a very good morning to the panel for today's presentation, Dr. Khairul Alsfa and Madam AMNI. My name is Nur INANI AMNI HUDA BINTI HAMREE from AS2446P, will presenting my thesis for final year research project entitled Genomic Analysis of Acinetobacter baumannii Genome Strings. Before I start going deeper, I will first give some brief introduction of my thesis. So, what is MDR? MDR, or multiple drug resistant, is a situation in which a pathogen is able to withstand drugs or chemicals of varying structure and function designed to eradicate the organism. While AMR, or antimicrobial resistance, is described as microbes' ability to survive and grow in presence of antimicrobial agents such as antibiotics, disinfectants, and food preservatives. Antibiotics resistance prevents the effectiveness of antibiotic use in healthcare, hence resulting in resistant development as time goes by. Moving on to the next slide, I will share to you about Acinetobacter baumannii, which is the bacteria that I used to analyze for this research. Acinetobacter is a genus of short pleomorphic coccobacilli from the Moraciliaceae family that are gram-negative, strictly aerobic, catalase positive, oxidase negative bacillus, non-fermenting and non-motile. This bacteria is commonly found in the environment, particularly in soil and water. Acinetobacter baumannii is a virulent bacteria that are able to cause pneumonia, urinary tract infections, skin and soft tissue infections, and nosocomial meningitis. Treatment alternatives are narrow due to Acinetobacter baumannii intense resistance, invading the host immune system, capable to live in biofilms and survive in extreme environmental conditions, making it being the most serious and frightening pathogen. Turning to the next key factor, which is bioinformatics tools that I use for this study. First is resistant gene identifier, or RGI. It is used to predict antibiotic resistance from protein or nucleotide data based on homology and SNP models. The application uses reference data from Comprehensive Antibiotic Resistance Database, or CARD. The next tool is ABRICADE. Given a FASTA contig file or a GenBank file, ABRICADE will perform a mass screening of contigs and identify the presence of antibiotic-resistant genes. It can compare input sequences against a comprehensive database of non-ARGs. I also use STAR-AMR to scan bacterial genomes contig against the ResFinder, PointFinder, and Plasmid Finder database and compiles a summary report of detected antimicrobial resistant genes. The last bioinformatic tools that I use is Fragmented Antibiotic Resistant Gene Identifier, or FARGene. It is a tool that takes either fragmented metagenomic data or longer sequences as inputs and predicts and delivers full-length antibiotic-resistant genes as output. Another important aspect to consider is the objectives. The main objective of this research is to analyze the resistant gene in Acinetobacter baumannii strings. Furthermore, this study also aims to make a comparison between 4 bioinformatic analysis tools for resistant genes detection. Bringing our focus to a new point, I will now outline the methodology I utilized to achieve my research objective. The first step is to collect the genome's data from various sources such as journal articles and databases. For this research, I used 50 different genomes to be analyzed. Next, the genome sequence was downloaded in FASTA format and uploaded to the Galaxy account. Then, select one of the genome contigs and start running the tools. The results will be generated after a minute or more depending on the length of the sequence and the internet connection. The RGI analyzed genome or proteome sequence under a perfect, strict, and loose aka discovery paradigm. The perfect algorithm is most often applied to clinical surveillance as it detects perfect matches to the created reference sequence in CARD. In contrast, the strict algorithm detects previously unknown variants of known AMR genes, including secondary screen for key mutations, using detection models with CARD's created similarity cutoffs to ensure The detected variant is likely a functional AMR gene. The loose algorithm works outside of the detection model cutoff to provide detection of new, emergent traits and more distant homologs of AMR genes, but will also catalog homologous sequence and spurious partial matches that may not have a role in AMR. Next, every kit produces a tab-separate output file with the following columns. The first column is the file name this head came from, and the second, the sequence in the file name. The third is the start coordinate in the sequence. Fourth, the end coordinate. Fifth, the strand either is positive or negative. Sixth, the AMR gene name. Seventh, what proportion of the gene is in our sequence. 8. The coverage map is a visual representation of the hit. 9. The gaps, which is openings or gaps in subjects. 10. The percentage coverage. 11. The percentage identity, which is the proportion of exact nucleotide matches. 12. The database used. 13. The accession number. 14. The product, if available. And last but not least is the putative antibiotic resistance. From this result, we can see that there are 8 in the detailed summary. A detailed summary of all detected AMR genes or mutation or plasmids or sequence type in each genome, 1 gene per line. Comparing all test results together, the RGI analysis tool showed the results of detecting the most antibiotic-resistant genes. Star AMR and every kit showed similar detection levels and FAR gene is the least. While the remaining 3 tools except Abricate use a single antibiotic-resistant gene database, Abricate used a complex antibiotic-resistant gene database used by other analysis tools such as NCBI, CGE, CART, and MegaRes. Next, even though FAR gene showed the least antibiotic-resistant genes, it is a suitable tool for researchers or students who want a specific criteria of gene